All right, welcome everybody. Today we're going to talk about lesson number 63, and this is a lesson about proofs and finding exact values. You'll remember that when we were doing proofs earlier in the chapter, I told you that they went away for about a week and then they will return. So here we are. You're going to be asked to prove each identity. While you're going to continue to use those same algebraic techniques like common denominators and hidden identities and factoring and substitution and all that good stuff, the reason why some people find these proofs much easier the second time around is because they are extremely formula driven. And by formula, I mean the sum and difference formula, the double angle, the half angle. If you don't find yourself using one of those formulas at least once in the problem, then that's kind of letting you know that you're on the wrong path, since that's kind of the focus here in the later half of chapter 5. So we're going to find also something called exact values, but we're going to save that till the end. So take a look at the directions, prove each identity. Remember, it can also say verify or show. And again, focus on the formulas. Before we go ahead and actually get into doing some proofs, let me just go ahead and try to give you a couple of tips and reminders. So far for each problem, we've mostly had one single variable, whether it was an X or a Y or a theta. Yes, we use different variables, but we didn't necessarily use them in the same problem. That is going to change right now. So you just have to make sure that you're keeping it straight. So for example, in the same way that sine squared plus cosine squared is equal to 1 for the variable x, please make sure that you know that sine squared of y plus cosine squared of y is also equal to 1. So as long as you have a matching variable for a sine squared and a cosine squared, it's going to be equal to 1 no matter what it is. And again, sometimes you have it within the same problem. In addition to kind of pointing out a couple things you should watch out for, I want to point out a couple of things that you should not do. These are some common mistakes that I would like you to try to avoid. The most common one and the most important one being the cosine of x plus y. If you were to find the cosine of x plus y, there is a formula that is not equal to the cosine of x plus the cosine of y. Not equal, not ever. There's a formula. It's a cos minus a sine. Please do not distribute. That does not work. If you make that mistake, unfortunately, it shows me that you know nothing about this unit, so don't be that guy. Something else I want to point out here, no. If you had the sine of 2x times the sine of x, these cannot be multiplied, at least not right now. So long as you have different variables, meaning you have a 2x and you have a 1x, you cannot not multiply those together. So please do not try to. Finally, again, another warning, do not, let's say you had the sine of 2x, let's say you have the sine of x in the denominator, these cannot be reduced. You cannot do 2x minus x. You can't cancel the signs. You can't cancel the x's. You cannot do anything so long as those variables do not agree. So again, maybe more than tips and reminders, it's just kind of a word of caution, things that you want to watch out for and be sure not to do. Sometimes that's just as important as the things that you should be doing. So let's take a look at number 1. You're trying to prove that the sine of pi over 2 plus x is equal to the cosine of x. Just like always, you're only allowed to use one side at a time. And again, you cannot move things from one side of the equal to the other. You cannot assume equality in order to prove equality. As I mentioned, this is all about those formulas. So taking a look at the sine of pi over 2 plus x, well, that is a formula if I ever saw one. So if you go back to your formula sheet, the sine of something plus something, that is this first formula here. It's the sine of u, the cosine of v, plus the cos of u times the sine of v. So the very first thing I'm going to do is I'm going to go ahead and, apply that formula. So here's my u and here's my v. According to the formula, this is going to be equal to the sine of the first thing, pi over 2, times the cosine of the second thing, plus the cosine of the first thing times the sine of the second thing. And again, u and v, all you have to do is look at the formula sheet and then plug those values in the right spot. The reason why we love problems like this is because I spy some unit circle values. I see the sine of pi over 2 and I see the cosine of pi over 2. Those are things that I know, so those are things that I'm going to sub in. If you calculate the sine of pi over 2, well, that's just equal to 1 times a cosine plus the cosine of pi over 2. If you substitute that in, that's equal to 0 times the sine of x. Well, I'm sure you remember that anything times 0, of course, cancels out, which means all you're left with is a cosine. Because that is what you were trying to make equal, you are now done. So again, yes, this is the first problem of the day, so it's a little bit easier, a little bit shorter, a little bit more straightforward. But generally speaking, people enjoy proofs this second time around, one, because they're a little bit familiar, and two, because they are extremely, extremely formula driven. So let's go ahead and take a look at number 2. The cosecant of 2x equals that right-hand side. Remember, you're still trying to determine whether you want to start left side or right side. In this case, it really wouldn't matter either way, but I'm actually going to go ahead and start the left side. So there is no formula for the cosecant of 2x, but I want you to realize that the cosecant of 2x is equal to 1 over the sine of 2x. So you are, in fact, allowed to use those reciprocal properties for any variable. Then, formula alert, the sine of 2x, if you look at your formula sheet, that is equal to 2 sine x cos x. So you're going to go ahead and make that replacement of 1 over 2 sine x cos x. Again, always keep your eye on the prize. The eye on the prize in this case is the cosecant over 2 times the cosine. I actually am done for the most part. I just have to make sure. So I'm going to go ahead and pull out the 1/2. Then I'm going to write this as 1 over cosine. And then I'm going to write this as 1 over sine. Well, if you take a look at that, you can definitely put the 2 and the cosine together in the denominator, and then 1 over sine. That's a formula. What formula? It's a cosecant, which means you are done. Remember, do something to let me know that you're done. Circle it, highlight it. I like to draw those double lines. And just FYI, if you had done this problem from the right-hand side, it would actually be this exact proof in reverse, which would be just as good. So again, left side, right side, it's really kind of up to you. Here in number 3, something interesting. We have the cosine of 3x. Now, interesting, if you look at your formula sheet carefully, we do have a whole lot of formulas on there, but unfortunately, none of them are 3x. And of course, based on what I just went over a few minutes ago, you would never, never, never try to cancel those signs or subtract those x's. You would never try to reduce them because you're not allowed to, right? Right. Okay. So clearly, if we're trying to equal 2 over on the right-hand side, then this is going to be a left-hand side situation. Again, if a formula is not the first thing you can grab onto, then think back to your other algebraic strategies. And in this case, it looks like the problem is telling me to subtract those fractions. Well, I know how to add and subtract fractions. I have to find a common denominator. So the common denominator would be a sine times a cos. You're going to multiply this sine of 3x times the cosine of x. So up top, that's going to give me the sine of 3x times the cosine of x. Then notice that it's a subtraction. Then you're going to multiply this sine times the cosine of 3x. So that is going to give me the cosine of 3x times the sine of x. So all I did was find a common denominator. And now, if you look really carefully at that entire top, you have sine cos minus cosine. That's a formula. So back to our formula sheet, you're looking for sine cos minus cosine. That's this one here. So that is the sine of u minus v. So if that is the sine of u minus v, then you're allowed to rewrite this as the sine of u, which is 3x, minus v, which is x. All right, well, 3x minus x, I can do that. That becomes a sine of 2x. And now remember, whilst you can't reduce those signs, hopefully you see here, this is yet another formula, the sine of 2x. The sine of 2x is equal to, per the formula sheet, 2 sine x cos x over sine x cos x. And because it's one big multiplication party, the sines are gone, the cosines are gone, and would you look at that, it's all equal to just a nice, simple 2. Oh, these continue to be one of my favorite things. I hope you agree. Just a couple more here. So number 4, there are not just one formula going on, but there's 2 formulas or several formulas. And again, always keep your eye on the prize. The eye on the prize is just that nice, simple tangent. Hopefully you would realize here that it would not make sense at any time to start on the right-hand side to try to make it equal to the left-hand side. So then try to find some formulas. I spy a formula up top, the cosine of 2x, and I spy a formula down low, the sine of 2x. So I'm actually going to start with the denominator only because there's only one choice for the sine of 2x. It's 2 sine x cos x. So there's only one to pick, so I'm going to pick it. Then I have 1 plus sine, and then I have a minus. Whatever I plug in here for the cosine of 2x is going to get that negative sign distributed to it. Now, the reason why that's important is because if you look at your formula sheet, there are actually 3 different versions of the cosine of 2u, which again is the same as the cosine of 2x. You want to try to choose the version that is the cleverest. While they will all eventually work, you want to try to choose the one that's the easiest. And maybe you don't see it yet, but the one that's the easiest is actually the middle one, 1 minus 2 sine squared. And here's why. The reason why you would select 1 minus 2 sine squared is all because of the ones. Because you have to distribute this minus, by choosing 1 minus 2 sine squared, the ones are going to cancel. And because I can see that, that's why I decided to go with it. So I'm going to go ahead and actually distribute that negative, which will give me 1 plus sine minus 1 plus 2 sine squared all over this big old denominator. Again, what was the whole point of that? I wanted to go ahead and cancel out those ones. So those ones are now gone. That is going to leave me with 2 sine squared plus sine over cos plus 2 sine cos. And again, keep your eye on the prize. Your prize is a nice, simple tangent. The only way you're going to be able to take this big old mess and turn it into a nice, simple thing is if things cancel. Well, nothing can cancel right now because of all the pluses and the minuses. The only way to get things to cancel, you guessed it, is to factor. So on the top, I'm going to factor out a sine of x. That is going to leave me with a 2 sine of x plus 1. On the bottom, I'm going to factor out a cosine of x, which is going to leave me with 1 plus 2 sine x. And your eyes do not deceive you. 2 sine plus 1 and 1 plus 2 sine, those are the same. Addition is commutative. So all you're left with is a sine x over a cos x. And would you look at that? That is a tangent. Oh, love it when that happens. So again, not just a single formula here, but actually several of them. So you always want to be on formula watch here. And then finally, let's take a look here at proof number 5. I also just want to point out here, while we haven't necessarily used some of the older identities as much, sine squared plus cosine squared equals 1, and the secant squared and the tangent squared, those are all still fair game. I picked problems today that focus on the new formulas, but please don't forget about the old formulas. They are still a thing. So finally here in number 5, because the right-hand side does look relatively straightforward, I'm certainly going to go ahead and start with the left-hand side. I spy not just one formula, but I spy a second formula. So because there are 2 formulas, I'm going to have to go ahead and do it twice. And then because there's just that nice addition sign in between, that's going to make my life a little bit easier. So starting with the cosine of x plus y, the cosine of x plus y, that's this one. You're going to have a double cos, then minus a double sine. So a double cos means you're going to have cos of the first thing times the cos of the second thing minus the sine of the first thing times the sine of the second thing. And again, just to reiterate, this entire thing is just the green formula. You don't distribute, you need the formula. Then you have that nice simple addition sign. And now you have to go ahead and do the pink. So the cosine of x plus y was double cos minus sine sine. Now the cos of x minus y is a double cos plus sine sine. So you're going to do plus cos x cos y, but then it's plus sine x sine y. And yes, it is the opposite signage, but that's just how the formulas work. So please don't make up your own. Please go back to the formula sheet. And then, of course, this is all still over sine x cos y. Well, look at that. Some good things are happening here. So the first good thing is this negative sine x sine y cancels out with this one. On the top, you're going to have 2 cos x cos y. You're just simply combining like terms. Then take a look. You have a cos y and a cos y. Those are going to cancel, leaving you with a 2. And then a cos x over a sine x. Well, that's just a cotangent x. So again, these tend to be a little bit shorter, a little bit more straightforward than the proofs from the first time around. So please make sure that you're looking for formulas when and if possible. Always go ahead and make that substitution. Okay, so the last thing I'm going to ask you to do for today is I'm going to ask you to find what's called an exact value. And please note that I'm only asking you to do it so far for the sum and difference formula. In the coming days, we will find exact values using other formulas, but today we're just going to focus on these. When it comes to finding an exact value, that means that no decimal answers will be accepted. It means you have to leave your answer in terms of radicals, so please make sure that you're aware of that. And here's what you're going to do. So I could ask you to find something like the cosine of 15. If you're going to use a sum or difference formula, you have to choose 2 values from the unit circle that either add or subtract to be 15. When you choose those numbers, if at all possible, choose one or both from the first quadrant. The reason why you want to choose the first quadrant is because everything is positive there, and that's going to make your life easier in just a minute. So cosine of 15, hopefully you would agree that 15 is equal to 45 minus 30. Sometimes I will give you those 2 values, and then sometimes you'll have to pick. More often than not, I'll just give them to you because it makes it easier if everyone has the same ones. But again, you could use any 2 values on the unit circle that add or subtract to be 15. You could do 330 minus 3. You could do 330 minus 315. You could do 315 minus 300. You can basically use any 2 values that subtract to be 15. But again, when at all possible, choose one or both from quadrant 1. So hopefully what you realize is this is really the cosine of u minus v. So you're going to go back to your formula sheet and you're going to choose the cosine of u minus v. So notice it's a double cos plus a double sine. So if I go ahead and plug that in, I am going to get that the cosine of 15 is equal to the cos of 45 times the cos of 30 plus the sine of 45 times the sine of 30. And again, this formula is from the formula sheet. Any formula that's a cosine, sum or difference, will be a double cos and a double sine. And it just so happens that you have the opposite addition or subtraction. So the minus formula is an addition. Again, no need to guess, no need to make up your own formulas. All you're going to do is use your formula sheet. And then you're going to literally plug in each of these values. So the cosine of 45, if you look at your unit circle, in quadrant 1 is positive root 2 over 2. Then the cosine of 30, which if you look at your unit circle, is positive root 3 over 2. The sine of 45 is root 2 over 2. And the sine of 30 is 1/2. So again, you're plugging those values in directly from the unit circle. So again, just to reiterate why this problem is so nice is because this is quadrant 1, where all the values are positive. That will not always be the case, which we're going to see in the next example. But again, when at all possible, choose one or both values from quadrant 1 because it just makes your life a little bit simpler. So now from here, you're going to go ahead and actually multiply these values. So when you multiply the square root of 2 over 2 times the square root of 3 over 2, you're going to get the square root of 6 over 4 plus 1 times the square root of 2 is the square root of 2. 2 times 2 is 4. You're going to get the square root of 6 plus the square root of 2 all over 4. And that's kind of weird and gross, but that actually is your answer. Again, when they say exact value, you have to make sure that you have no decimals. You have to have just some combination of radicals. Now, here's the good news and the bad news. The good news is that you are always going to wind up with some version of this answer because you're limited in the exact values that you can find. 15 can easily be found with unit circle values, but I couldn't find the cosine of 10, or I couldn't find the cosine of 20, or I couldn't find the cosine of 100. I can only find values that can be added or subtracted to use the sum and difference formulas. So again, the good news is you're only going to get versions of this formula, but the bad news is it winds up being kind of boring because of the fact that you're only going to get a handful of solutions. So that also means I'm not going to have you do too many of these because if you can do a couple, you can do multiple. Okay, and then our final problem for today is we're going to find the tangent of 195. And again, today we're only using sum or difference formulas. So we're going to go ahead and do 225 minus 30. Remember, again, there are multiple combinations that could equal 195, but I'm going to have to choose at least one of them, not in quadrant 1. So that's why I made sure to pick 30, where everything will be positive, and then I picked 225. So this is the tangent of u minus v. So again, pull up your formula sheet. This is the tangent of u minus v, so I have to make sure that I'm using the right formula. So subtraction on the top and addition on the bottom. So first I'm going to start by writing the formula. So this is going to be equal to the tangent of 225 minus the tangent of 30 all over 1 plus the tangent of 225 times the tangent of 30. So I'm going to have to know the tangent of 225 and I'm going to have to know the tangent of 30. So just to write them over here as a reference, the tangent of 30 is positive radical 3 over 3. The tangent of 225 is in the third quadrant. So it's actually a positive 1. Again, it just makes life easier if you're able to choose positives whenever possible. But I guess if I'm choosing for you, then you kind of just have to go with it. And again, if you're wondering where I got these values, they're from the unit circle. So I'm going to go ahead now and actually sub in those values. So for the tangent of 225, I'm going to plug in a 1 minus root 3 over 3 for the tangent of 30. And then 1 plus 1 times root 3 over 3. I'm going to go ahead and find common denominators in the top and bottom. So here in the numerator, this is 1 over 1. So the common denominator would be 3. So this is going to be 3 minus radical 3 over 3. Then this is 1 over 1 plus root 3 over 3. So I'm going to find a common denominator of 3 in the bottom as well. And that's going to be 3 plus radical 3. If I go ahead and want to get rid of the complex fraction, I'm going to do the keep change flip. So 3 minus radical 3 over 3 times 3 over 3 plus radical 3. The 3's cancel. And I'm going to be left with 3 minus radical 3 over 3 plus radical 3. I know it's a lot of 3's. In the final step, just like always, you are not allowed to have a radical in the denominator. So you're going to have to just go ahead and rationalize. So how do you rationalize 3 plus the square root of radical 3? Well, you're going to multiply by 3 minus the square root of 3. And again, 1 on the top and 1 on the bottom. This is rationalizing the denominator. So on the top, I'm going to have to go ahead and do the full FOIL. So 3 times 3 is the first, which is 9. Outers is negative 3 radical 3. The inners is also negative 3 radical 3. So that's a total of negative 6 radical 3. Then the last is negative radical 3 times negative radical 3, which is positive regular 3. On the bottom, because I am doing conjugates, rationalizing, I only have to do first and last. So 3 times 3 is 9, minus root 3 times root 3 is 3. Little bit of simplifying. So 9 plus 3 is 12 minus 6 radical 3 all over 6. And then because all of these values can be divided by 6, I'm going to go ahead and do so to give me a final answer of 2 minus radical 3. Now, just like the previous problem, there's good news and bad news. The good news is that because we only have a handful of values that we can use, you are always going to wind up with some version of 2 minus radical 3. The bad news is you're going to have to repeat that process because it's always going to look very similar. Again, I think these problems are kind of boring. You only wind up with a handful of answers, so I'm not going to have you do very many of them. So all done for today. That brings us to homework number 63. Please make sure you note that homework number 63 takes place in 2 sections. Most of these problems are proofs. The only one that is not is number 8. Number 8 asks you to find exact values, and it asks you to do the sine, the cosine, and the tangent. So that's what I mean when I say be sure to do all 3 parts. So thanks very much for tuning in, guys, and we will catch you next time.